Oh, because of the Alberta connection? Is that?
I mean, yeah, that's how I started like inviting people to the talk because I saw Laura's name on your guys' list of potential speakers, and I was like, oh, I know her. That would be kind of fun if she gave a talk. Um, so yeah. All right. So thanks everyone for joining, and thank you, Laura, for also coming with us. And so today, oh wait, re-recording? Should I go? Yeah, it is streaming. Okay. Yeah, so today for the robot learning seminar, we are joined by Laura Petrich, who is a Ph.D. student at the University of Alberta, where she works with Dr. Patrick Pilarski of the BLINC lab and Dr. Matthew E. Taylor and the IRL lab. She previously received a Bachelor's of Science with Honors in Computer Science from the University of Alberta in 2019 and her Master's from U of A as well in 2022. And her research interests include neuroprosthetics, reinforcement learning, human robotic interaction, and assistive robotics. And she draws a lot of her inspiration from anatomical studies with Dr. Pierre Lemelin. And her research right now aims to develop control methods for robotic manipulation with the goal of increased functionality, usability, and blah, blah, blah. And so today she'll be giving us a talk about her research and some of the big picture things about prosthetics, I believe. So thank you again, Laura, for joining us. And the floor is yours, I guess.
Well, thank you for that lovely introduction and thanks for having me. Let's see if I can share my screen properly. Okay. How's this?
Right. Crystal clear.
Cool. Okay, welcome to my talk. I'm Laura, and I'm going to be talking about becoming bionic, so prosthetic limbs. Like Michael said, I work with Patrick Pilarski at the BLINC lab, which stands for Bionic Limbs for Improved Natural Control, as well as Matt Taylor with the IRL, so Intelligent Robot Learning Lab at the U of A. Okay, so here's just a kind of high-level overview of the talk I'm going to give. First, we're going to talk about kind of neuroprostheses and the problems that we are trying to solve in this space, as well as what other peoples are doing to try and solve them. And hopefully by the end of this talk, you have a general idea of what's going on in myoelectric prosthetic control. I'm going to end off on a study that I'm currently doing in my research and what we hope to accomplish with it. Okay. Okay, so first let's just talk a little bit about AI and machine learning in medicine. So there's a couple of things that we are interested in and we want to understand. So we want to understand how we can help populations in general. So this is kind of like a generalization problem. We are also individually focused. So not only do we want to build models that are able to generalize to a whole population, but we want to be able to individualize them to specific people based on their needs and wants. We also need to understand how we can choose and improve these different interventions, either by connecting patients with the assistive devices or helping to deploy treatment strategies. At the BLINC lab, we work really closely in collaboration with the Glen Rose Rehabilitation Hospital here in Edmonton, so we can test out all of the things that we are creating in the lab directly with patients and then get their feedback to try and close that loop to make sure that we are always focused on improving quality of life for individual patients. Okay, so here at the BLINC lab, we are all about prosthetic limbs. We are focused on creating new smart prosthetic devices with the intent of improving quality of life for those with both upper limb and lower limb differences. So we have new bodies, new skills, and this presents new challenges in prosthetic research. So you guys are all about robotics. So you've probably seen all those videos on YouTube and out there on the internet about all these cool high-tech multi-articulate hands that are now available. So They have individual digits that can be individually controlled. We're able to connect them to these like research wands in order to test things out. There's even companies like Bionic that have these apps that you can have on your phone. So they can pick up on the different motions that you make with your fingers, and then you can control each of the digits individually. So this is awesome. But in practice, if someone with limb differences were to take one of these home, they actually just come with a set of predetermined grasps that they can choose from. So there are no, as far as I'm aware, any prosthetic devices for the upper limb available where you can attach it to the person's residual limb and control the fingers individually. So not only do we have this problem with being able to control the digits individually, but everything that we develop in prosthetics has to be able to be housed on the device. Everything needs to be lightweight and compact, and you can't have really high compute needs. So you can think about it that individuals don't want to be able to carry around backpacks with them or have to be tethered to a computer. Everything needs to be on the limb, and you want it to be roughly the same weight as their other limb. So when we talk to actual prosthetic users, and this is a really great article on the internet if anybody is interested in reading it. So when we talk to actual prosthetic users, there's a really strong feeling in the community that the prosthetics industry is too focused on developing these really high-tech hands and that they aren't actually functional in the real world. So we're missing that connection between what is going on in the research lab and what is actually being deployed and used in the real world. This leads to a huge problem with device abandonment. So some companies, such as TRS, offer simple prosthetic attachments that can be controlled through body-powered cables instead of myoelectric control. I'll go into myoelectric control in a minute. So this is often faster and easier and more reliable for the user to use. Also, look at all the cool hands that you can get. So this kind of works like you can just like clip it on and attach it when you want to switch out the activity that you're doing. But then, of course, you have to carry the hands with you everywhere that you want to go or prepare in advance for what you want to be able to do. Okay, so in this talk, I'm going to be talking about 3 different problems as well as what we are doing to try and solve them. This leads to our first problem, device abandonment. So it is known that non-intuitive control of these prosthetic limbs represents one of the main reasons that amputees stop using their myoelectric prosthesis. So that leads to my first question. How can we increase the functionality of these devices? But first, let's take a step back and ponder what actually connects the person and the machine or the prosthetic device. Are we able to engineer this connection? Or do we need to think differently? Okay, so let's talk about human and machine intelligence. What exactly is intelligence? How do we know how to go from data to our goals? How do we know what is the right decision to make? And how do we know even what decisions need to be made? So this leads us back to the 3 things that we always talk about in robotics. So we have in the sciences, we have observe, explain, predict, and control, right? Or maybe in cognitive science, we talk about perception, action, cognition. Or in computing science, we talk about representation learning, right? And then prediction and control. So these are all different words for essentially the same thing and how we go from our input data to the goals that we want to achieve. We need to be able to perceive the environment around us. We need to be able to take that knowledge and make predictions about what we want to do. And then we need to be able to act on those decisions. So, surprise, surprise, machine learning. These things can all be learned and continually improved by a machine. Okay, so we have these cool high-tech multi-articulate hands that are now available, and people can buy them. They cost a lot of money, but you can still get them. So most commonly, they rely on myoelectric control in order to use them. So what is myoelectric control? Myoelectric control picks up on the signals, the electromyography signals that are being sent to the muscle. So essentially, you can think about it, your brain, you think, okay, I want to be able to close my hand. The brain sends a signal to that muscle, and then the muscles that are involved in closing your hand, they contract and your hand closes. So EMG signals are able to pick up on that muscle contraction, and then it gets mapped to the motion of the robotic hand. This is generally done through some sort of pattern recognition in machine learning, so essentially supervised learning. Okay, so now I'm going to start talking about my research a little bit more. So on the perception side of things, we are focused on right now for transhumeral limb difference. So this is if someone were to have an above elbow amputation. So when you think about it, for transhumeral limb difference, you have above elbow amputation, you are left with your biceps brachii and your triceps brachii. So you have two input signals. You can also co-contract them, but you still have the two input signals. So how do we go from these two input signals to a multi-degree of freedom robotic limb? That is one of the main questions that we are trying to answer. And depending on your level of amputation, so if you have a below elbow amputation, which is called transradial, then you'll have more input signals because you have more muscles down there that you can pick up on. And then you only have to deal with the wrist action and then the hand, right? But you still, if we have the ability to control all the digits individually from a hardware point of view, you still have trouble mapping those signals to all the digits of the hand. Okay, so this is the perception side of things. How do we pick up on those input signals? Say we're using electromyography signals, so EMG sensors. We have two signals to play with. So that leads to our problem number 2. We have this low to high dimensionality mapping that we are trying to achieve. Which leads me to the question, how can we increase the input dimensionality? And if we were able to increase the input dimensionality, can we perceive the new signals? Also, if anybody has questions at any point, please feel free to pause me and ask them. Okay, so let's just talk about how prosthetic limbs are attached to the residual limb. The residual limb is what we call the amputation. So generally, when someone is fit with a prosthetic limb, they will go to a prosthetist and they're made a custom fit socket. This involves 3D modeling of the residual limb. And while they do help to attach the prosthetic limb to the residual limb, they come with a number of problems that can also lead to device abandonment. They can be uncomfortable to wear, and as the person's muscles changes, or if they get sweaty or hot, then the fit doesn't work as well. They have problems with slippage, and maybe they need to take it off and readjust the socks that they wear underneath them. There are rubbing problems that can cause the skin to break down. And if we're thinking about it from a control point of view, they also make it difficult to place EMG sensors on the residual limb. If you look here at the picture, you can see that the custom fit socket that this man is wearing covers up all of his residual limb. So in this case, if it were being mapped to a myoelectric prosthesis, the sensors would be fit actually inside the arm. And then sometimes there's problem with the sensors not placing or pressing properly onto the muscles, or maybe they shift slightly if they're being placed differently, or if the person's moving them and the harness makes it shift. So this is one of the problems that is faced in myoelectric control. Okay, so that leads me to my third problem, that there's limited real estate for sensor placement. Ideally, we wouldn't want to put these sensors within the socket. We would want to be able to place them outside the socket. But if the socket is covering up the entire residual limb, we can't do that. So, can we free up space on the residual limb? All right, so we have our 3 research problems that we are focused on. Problem 1 is our device abandonment. So we know that we want to increase functionality of these devices through more intuitive control, and that this increased functionality will hopefully lead to reduced device abandonment. So how do we do that? Well, we can do that by addressing our problem number 2 and problem number 3. If we have the low to high dimensionally mapping, we can actually use targeted muscle reinnervation, which I will go into depth here right away, to increase the number of input signals that we have. For problem number 3, the limited real estate for sensor placement, we can actually do a surgical intervention called osseointegration in order to free up that space. So here's some progress on our home front at the BLINC lab at the U of A. We are changing the body in order to change the machine to change the body, which sounds like a fun little loop. So what is osseointegration and targeted muscle reinnervation? So this is a surgical intervention that we are doing in the lab. The past few years, we've been focused on the lower limb, but now we're going to be working on the upper limb. So osseointegration is actually the process where we surgically implant a steel rod into the remaining bone. It's called an abutment, and then the prosthetic limb can just be clicked right on. So that frees up space on the residual limb. We can now place sensors wherever we want. Targeted muscle reinnervation is also a surgical technique. So if you think about it, we have our biceps brachii, right? It's called the biceps because it is actually 2 distinct muscle heads for bi. Triceps has 3 distinct muscle heads. So you can surgically go in, separate the 2 heads of the biceps, remove the nerves that are innervating it and providing motor control from one of the heads, and then reroute a nerve from the forearm to the remaining head. So in this way, we can actually get up to 5 distinct input signals to use for our control systems. So we've been doing this targeted motor and sensory reinnervation in the lab for a number of years now. And we've had great success. We can then use machine learning to streamline limb control because we have more input signals that we can feed as the input vector into our machine learning models and be able to differentiate between more actions. Let me just check on time. Okay. We're doing well. Oh, sorry. I need to unmove this.
The shaft.
Can you hear that?
In the center of my bone, and it goes all the way up to here. And that's the simplified version of it. And this is how fast it comes off. Literally that fast. And it attaches in here. And this is one of the features of having osseointegration is that I can rotate it. So, and then to put it back on, it is literally on. It's that fast. And that's one of the nice things about osseointegration is that saves so much time compared to with a socket and taking so much. The fastest I ever could put my socket on was 5 minutes. That was the fastest. And that was not guaranteeing it was even going to be straight. Sometimes with the socket, in the middle of the day, you'd have to stop and take it off and change and put more padding in and stuff just to make it fit properly or take padding out. The more you'd overwork it, the more you would pay at night when as soon as you took the socket off, it would be all blisters. Whereas now I don't get that. I don't get, even if I do overwork it, it's because the rest of my body is tired, not just because my leg is tired. I still have to be careful with it that I don't over twist it. So there goes my hockey career, which I didn't have one before anyways, but that's besides the point. But overall, it's so much better. This gives me more time to spend with the family and more quality time at times because instead of being home and just laying down and just being right tired, I have more energy left for the family a lot of times. And I'm not saying that I still don't go home and lay down for half an hour or something like that just to recuperate a bit. But it's overall, I do have more time for family, for other activities.
Okay, so that was one of the previous patients that have come through the lab for osseointegration of the lower limb. So we've had great success with the lower limb, and are now moving to the upper limb. We're going to be the first lab in all of Canada that's offering osseointegration and targeted muscle reinnervation for transhumeral limb differences. So this leads me to my own, the research that I've been working on since starting my PhD. So in order to be able to build machine learning models for our target population is someone who has transhumeral amputation, osseointegration, and targeted muscle reinnervation. Over the next 6 years, we will have, I believe, 6 individuals coming through doing these surgeries that we will be developing new control systems for. We are addressing a number of research problems through this targeted muscle reinnervation data collection protocol that we started. First of all, there aren't a lot of people in the world who have had these surgeries. So there are no data sets available in order to train these models are. We also have limited access to individuals who've had these surgeries simply because there aren't a lot of people who've had them for the upper limb. It is a very cutting edge surgical technique, and there's only a few number of labs in the world that are doing this. We also address the limb position effect for transhumeral amputations. So one of the other problems that I haven't talked about yet with myoelectric control is that they work fairly well if you're doing tasks kind of right in front of you. And you think about if I'm picking up a cup from the table or something. But as soon as you're trying to do something with your arms above your head, you can think about it, your muscles are being pulled over your shoulder joint. Everything is shifted. Their performance degrades substantially. So this is called the limb position effect. When your limb is in different positions, the model performance degrades. And so another student, Heather Williams in the BLINC lab, has been working for her PhD on solving the limb position effect for transradial amputations. And we're now working on solving this for transhumeral amputations. So we developed this data collection protocol so we are able to collect data on individuals without amputations that will generalize to this patient population. Because as we know, machine learning models are very data hungry. We need a lot of data in order to train efficient models. So we do this by choosing specific sensor placements in order to pick up on the underlying innervation pattern that will match an individual with this targeted muscle reinnervation. This will enable us to gather training data ahead of time on individuals without amputation, as well as reduce the training burden on the end user and improve model generalizability. Okay, so I'm going to talk about the protocol a little bit. So down here at the bottom, we have all the limb positions that we are collecting data in. There's 13 of them total, which cover the entire reachable workspace of the human upper limb. In each limb position, we have our participants go through all the actions of the upper limb. So rest, elbow flexion and extension, supination, pronation, wrist flexion extension, radial and ulnar deviation, as well as hand open and closed. So in each of these limb positions, for each action, we have the individual hold the action while we collect EMG data as well as accelerometer data. So we have them do this bilaterally. We brace one of the arms so that we're able to see the difference between isometric and isotonic contractions. So when either the muscle is moving over the joint when it is being moved or it's not. And in doing so, we get this beautiful data set full of rich EMG signals and accelerometer signals that we can then use to train our machine learning models. So in the fall, we carried out a 3-person pilot study and analyzed the data and then submitted a paper to the Myoelectric Control Symposium that we are just waiting to hear back on, fingers crossed. So essentially, we came up with this targeted sensor placement in order to pick up on the underlying innervation patterns. And feel free to pause me if you have questions, because this can be really information heavy. So here on the y-axis of this little chart, we have all of the actions of the upper limb. Along the x-axis, we have all of the muscles that we have chosen to place sensors on. So we are looking for muscles that are, first of all, close to the surface, because they need to be close to the surface in order for the EMG sensor to pick up on the signal being sent. We are also looking for muscles that match up with the nerves. So in targeted muscle reinnervation, we have these three main nerves of the forearm that are being mapped back up to the residual limb. So remember I was talking about the biceps brachii. We have the short head and the long head of the biceps brachii here. Can you see my pointer when I'm pointing on my slides?
Yep.
Yes.
Okay, cool. Thank you. Okay, so the short head of the biceps brachii in targeted muscle reinnervation, it gets de-innervated. It's natively innervated by the musculocutaneous nerve. So the musculocutaneous nerve is coming and it's going to send signals to the two heads of the biceps brachii, and then the biceps is going to contract. During targeted muscle reinnervation, we remove the motor nerves that are going to the short head, and we reroute the median nerve that would be going to the forearm up to the short head. So now, when you're thinking about doing wrist flexion, which is generally done by the muscles that are innervated by the median nerve, your short head of the biceps brachii is then going to contract. The same goes for the triceps brachii. So we have the long head and the lateral head. So we remove the motor innervation from the radial nerve that would be going to the lateral head of the triceps brachii. And then we take the deep branch of the radial nerve and we move that back up here. We can also do the same with the ulnar nerve to get that fifth muscle sensor, or that fifth signal. It goes actually to the brachialis muscle, but that lies deep to the biceps brachii. So we can't pick up on it because it's not close to the surface. But in someone with amputation, it will lie close to the surface because they move it closer during the operation process. So that's why there isn't a darker line coming off the ulnar nerve here.
Laura, there's a question in the chat.
Oh, yes. I will open that up. Okay, more of a high-level biomechanics question to refine my understanding of the problem. Can these signals be identified earlier in the main nerve, closer to the spine, before they specialize into all of these minute signals? Oh, that's a great question. So yes, they can, depending on the nerve. So the radial nerve, if we're thinking about this one, it actually is coming along and then it splits into the superficial and deep branch. So for the radial nerve, it is actually the same nerve going down the arm and splitting. So for that one, we would want to take, if someone has amputation, then we take the end of the radial nerve as far as we can. We reroute that one. For the other nerves, they are distinct nerves that branch up here right in the brachial plexus, which exists in your armpit. So for that one, you could take a earlier branch. This picture is showing for someone with out amputation down here, that's where you would place the sensors. But for someone with amputation, this part of their limb has been removed. So you are taking a closer portion of the branch and rerouting it to the muscle. So I guess long answer to your question, or short answer, yes, you can. If that makes sense. Thank you. Okay, yeah. So you can, now let's look at this little chart up here. So the triceps brachii is responsible for elbow extension. So that's why we have these dark colored squares here. Everything is color coded so you know which nerve is innervating it. And then this little light blue nerve ending in here is denoting what nerve gets rerouted after targeted muscle reinnervation. These slightly shaded squares are where we anticipate noise in the EMG signals, or slightly lower levels, because it is either a action that the muscle is helping with, or it's due to its close proximity. Okay, so then these signals in pink, these are what would make up our 5 input signals for a machine learning model, because this is the 5 input channels that somebody with targeted muscle reinnervation would have. Is there another person in the chat? Oh, thanks. You're welcome. Okay. Okay, so our results. We collected data on 3 pilot participants, and then we took all of the data from all the participants and combined them to create these heat maps. So these heat maps essentially show us, for each column, a ranked mapping of where you find the highest signal to the lowest signal. So from this, we have the braced arm, which is isometric contraction. So that's where the muscle does not get pulled or change length as the action is happening. So you think about it, if your arm is braced like this, and then you try to do elbow flexion, your elbow is going to stay in the same space. And then we have isotonic contractions on the unbraced arm. So that is where your elbow, the joint would actually move. So your muscle is changing length. We do see the same patterns start to emerge, which is kind of just a sanity check for us to make sure that our sensor placements are picking up on distinct EMG signals that a machine learning model could use to differentiate between the actions. So you can think about this as like, okay, if you see one row would be sent as your input vector, are the rows distinct enough that a machine learning model would be able to predict the pattern? Or if it sees a similar pattern, can it predict that that pattern would be, say, elbow flexion or pronation? So our kind of key takeaways from this study. We know that targeted muscle reinnervation is a promising avenue for opening new and intuitive methods for myoelectric control. It increases the number of input signals that we have available, and so we should be able to train better performing and more reliable machine learning models. This work offers 3 key contributions to the field of advanced prosthetic control. First of all, we introduce a bio-inspired protocol for collecting data in 13 different limb positions targeted at training machine learning models for persons with transhumeral amputation that have undergone TMR surgery. By analyzing these different muscle activation patterns, we can anticipate which actions the machine learning models should be able to accurately predict for users. The study also touches on the limb position effect because we included 13 different limb positions that cover the entire reachable workspace of the human arm. These limb positions are reflected in the data and enable us to further analyze the effect of limb position on muscle contractions. Our protocol also captures the difference between isotonic, the unbraced arm, and isometric, the braced arm muscle contractions. This will be of particular interest when comparing with data from users in future investigations. So this last one I didn't talk about too much. So there's kind of an established assumption in the field of prosthetics that people with amputations are the signals that we get for them are closer to isometric, so the braced arm, than they are to the unbraced arm. So this is kind of just assumption that we have in the field, but this study and data collected using this protocol will actually give us a quantitative way of establishing whether this is true or not. So in conclusion, this work presents a novel data collection protocol for TMR prosthesis control. It uniquely reveals the interplay between limb position and muscle activation while capturing the differences between those different muscle contractions. This sets the stage for training limb position aware prosthetic control models and offers the flexibility to use data from persons without amputations for training these models. Hopefully, our approach has the potential to help streamline the development of new targeted muscle reinnervation ready control strategies, as we're going to be doing these studies over the next 6 years. So the next 2 years, this is what we're going to be working on. This next summer, we are doing a full study to do using this data collection protocol, including individuals with transhumeral amputations. So we will be able to test some of the assumptions that we made. We're also working on investigating new control models for online continual learning. and then mapping this model output to prosthetic control. This is especially relevant in prosthetic control because of the device abandonment and performance degradation over time. So if you think about it, we as humans are continuously changing. Our muscles are always changing, whether we're fatigued or whether we've gone to the gym that day. Our muscles are constantly growing and shrinking, and whether we are outside in the rain and then we get wet. So it would be really helpful to have prosthetic control methods that are able to learn online as a person is using their device. We are also doing these osseointegration and TMR surgeries, and we hope that this together, our goal, this will lead towards improved functionality and reduced device abandonment in the field. So you are already becoming bionic. How many of you have a smartphone or a smartwatch? Do you ask the favor of ChatGPT or Gemini when you're working on your things? We are all becoming bionic, and intelligence is now the amplifier. We're at a turning point in civilization. Our bionic parts are all the smart tools that we use in our everyday life, and they present with the hallmarks of intelligence. So thank you for listening and being here with us today. If you would like more information or want to chat about any of these things, please contact me. Here's my email, as well as you can check out our lab websites here. Thank you.
Amazing. Is there time for questions?
Yeah, I have time.
Yeah, so I guess I was thinking about the continual learning machine learning problem, which seems like actually really, really interesting. So, but I want to make sure that I also understand the biomechanical side of it. So the actual system that you're trying to control is actually changing over time, is the argument that you're making, because the actual muscles that you're using to read the signals from are changing over time.
Yes.
And so the way that you want to map the brain signals to the actual control of the prosthesis should depend on that. It should take that into account. That's what you're...
Yeah, essentially, it should take that into account. And instead of us seeing these, so like right now for pattern recognition models, they train the model and then they freeze it and then it's deployed on the device. So if the person changes or if they need to go through these retraining routines every time their performance starts to degrade. So if we're able to have online continual learning built into the device that they're able to take home with them, it would completely remove the need of these retraining times that the person has to go through. So
why is there a performance degradation over time?
So it's in part due to the person's muscles changing, or every time they put on their prosthetic limb, it's placed slightly different, or if it is slipping as they're using it throughout the day, or if the sensors aren't making as well of contact with the residual limb. There's a number, a lot of those things we can't help with on the software and control side of things, but some of them we can. So if it's continuously learning from the data as it's gathering it, then it can put that into the training set when it updates the model. So then it will have seen those samples where, say, the person has a sweaty arm. So the next time the person has a sweaty arm, it'll be able to still make accurate predictions.
Yeah, so I guess what I'm getting at is so in the continual learning literature, there's this catastrophic forgetting thing where you don't want to have forgotten how to do things that you learned a long time ago. But then there's also the online learning case or adaptation case where yeah, your thing just needs to adapt over time because the actual underlying thing that you're trying to model is actually changing, and you don't really need to care about being able to go back to something that you had before, imagining aging, for example. As a person gets older, you could imagine that your model doesn't have to be able to it can forget how it did it when you were 20 because you're never going to be 20 again, right? Yeah, so I guess I don't know. It seems like there's this combination of these two things that's very interesting because, like, in some sense, it's like these repeatable situations, like being wet or sweaty or other things that might happen again. But then there's also this sort of like gradual progression of the actual human body that's also going on that requires adaptation. Anyhow, I don't know. It sounds very, very interesting problem, I think, from like a machine learning standpoint.
Yeah, I agree completely. And actually, that's a really interesting point that you brought up about like as we age, do we really need to remember the tasks that it was able to predict when you were, say, 20, when you're 70, because your muscles are no longer the same and they're not going to go back to being the same. So like maybe we need some sort of like adaptive degrading over time continual online learning model.
Mhm.
I will definitely be giving a seminar within the next year on online continual learning in prosthetics because we've been investigating these new type of models for that I think are going to be really promising. So
Cool.
I can let you know when that's happening.
Sure. Yeah.
I also have a question related to the signals being identified closer or earlier in the nerve that
Mhm.
I asked earlier. Um, I if I understand correctly, part of the problem is that the muscles shift lower in the limb, so that your sensor captures different information depending on when the muscle has shifted, if you've gone to the gym, whatever. So, is there like why don't we capture signals earlier in the spine so that there's less shifting since it's more static, more bony, I guess?
Oh, like actually collecting signals from the spine. So there
Like,
there are research groups that are working more on like the brain computer interface where they can use like EEG caps in order
mhm.
to pick up on the brain signals directly rather than waiting until they go to the peripheral nervous system, which is what we are picking up on placing sensors on the limb. So there is a lot of research being done for that. At the BLINC lab, we are really focused on developing systems that can be taken home and used in our everyday life. So
Right.
there are no take-home EEG brain computer interface systems, nor do people want to have things on them that are like bulky and intrusive in their everyday life. They want something sleek that they can just kind of like, it's hidden in the prosthetic limb if they don't want to show it off, right?
Yeah.
So using EMG signals is a very non-invasive and method of picking up on the input signals directly at the device. And then you don't have to worry about like wires that could get tangled or anything like that. So it is just a choice that our lab has made to focus on.
Okay, I understand.
Thank you for your question.
Any other questions? Anyone?
I have one other one
Sure.
that's unrelated. When you install a prosthetic limb, I assume like surgeons perform specific standardized uh, amputations such that, most limbs match up pretty well from patient to patient. But I assume some patients need basically custom prosthetics. So is there some kind of aspect to the learning algorithm that adapts between different, I guess, prosthetic limb morphologies, for example?
That's a really good question. So as far as I know, actually everybody is fit with a custom prosthetic limb because the level of amputation, if it isn't congenital, so if it isn't from birth, then it really depends on the accident that they had. And in that case, they try to preserve as much of the limb as possible. So the level of amputation differs depending on the individual and what they went through. So anyone who has gone through an amputation will go and get fit by a prosthetist with a custom device specifically for them. So all of the hardware is highly individualized. And then while we're interested in training generalized machine learning models, I didn't really go into the fact that when you then map that into like deployed real life situations, we will likely have to do like start with the generalized model and then do some sort of transfer learning or train the last layer of the model in order to individualize it to the specific patient based on like, say, their input signals. So like if someone has transhumeral amputation, but it's higher up, closer to the shoulder, then they're not going to have the brachialis muscle left. So then we will only have 4 input signals. If they have a longer residual limb closer to their elbow, then they'll have that muscle and we'll have 5 input signals. So really we can only do so much trying to plan ahead on what someone will need that has gone and had this osseointegration targeted muscle reinnervation surgery. But then once that patient is working with us in the BLINC lab, we will customize whatever model they need to the specific situation that they have.
And I guess as a follow-up, like for example, in the example you mentioned where there's 5 input signals versus 4, how do you specialize a model with 5 inputs and to only take 4 inputs? No.
So we would probably have 2 different machine learning models where we train one that has 4 inputs and one that has 5 inputs, and then use that as the base model when we're starting to individualize to that person.
Okay. Makes sense.
Yeah, we don't want to change the input dimensionality.
Yeah. Okay. Cool.
Thank you.
Cool. Thanks.
You're welcome.
Very cool problems.
It's super fun. I am absolutely loving it.
Question, Laura?
Yeah.
Yeah, because you mentioned that your solution for problem 2 is like increasing the biological number of inputs. And I guess, have you seen, or is it of any interest in the BLINC lab, or, you know, kind of maybe trying to use machine learning to compensate the other way? So maybe, I don't know, for some reason, as you said, maybe you only have 4 inputs, but, you know, you have a robot hand, there's all these DOFs you want to control. Maybe using machine learning to try to compensate for the fact that you can't keep increasing the number of inputs. Is that? I'm biased just because that's my own research. So, you know, I'm curious what the BLINC lab's doing in that direction, if anything.
Yeah, no, that's a great question, Michael. We should collaborate on that. But yes, you can use machine learning. So I didn't really go into this, but one of the conventional ways of, so if you have 2 input signals and you have, say, elbow flexion extension, wrist flexion extension, and hand open close, you have 3 kind of actions of varying degree that you're trying to map it to. So traditional control systems would say, okay, if you flex your biceps, your elbow flexes. If you contract your triceps, elbow extends. And then if you co-contract the 2 of them, then we're going to switch. We're going to mode switch to the wrist joint. So then when you contract your biceps, wrist flexes. Contract your triceps, wrist extends. Co-contract both the muscles, and now you're controlling the hand. So biceps, hand closed, triceps, hand open. So you use this mode switching as you kind of cycle through the set of actions that you have available. In the BLINC lab, they've developed this machine learning kind of solution for this problem called adaptive switching. So then instead of having this set cycle of actions you're sweeping through, they use adaptive switching in order to predict what is the most likely action the person will want to use next. So there are different things that we've done in the lab. And that's just one example of how machine learning is used without increasing the number of input signals available.
I see. I guess kind of I'm very confused because I don't know anything about biomechanics or biology, frankly. So with these EMG signals, I guess I'm having a hard time trying to wrap my head around like activating, I guess, independent muscles to indicate like an input signal.
Wow.
So it's kind of like, okay, so you do the surgery that remaps a nerve to another bicep head. So then does that mean, like, I guess if the person thinks about like, I can't remember which body, but like activating the part of the limb that's not being used, they're actually going to flex only one of the bicep heads independently of the other head, for example. That's like the byproduct of the surgery in this concept?
Yes, But it's not as straightforward as I made it out to seem in the presentation. While the nerve now reinnervates that head, the person does have to train and practice using their muscles and like almost like that brain rewiring thing that we have. Like we're very plastic. We can learn to adapt. So you have to go through a whole training process where you learn to use your newly reinnervated muscles.
I see. And even without this surgery, is that a big problem that I guess people living with prosthetics have to deal with? Because I don't know, I kept flexing my arm and I was having a hard time trying to imagine very easily switching between like activating bicep versus tricep. And so is that just like part of the process that everyone with prosthetics has to go through, is kind of getting used to this notion of consciously thinking subsets of muscles? Okay.
Yeah, and it gets easier over time as you get used to it.
Cool.
Yeah.
There's no more questions. Guess let's thank Laura again for making the time for this.
Thanks, Laura.
Thank you for coming.
Thank you for having me.
Thanks so much.
Yeah, and if anyone wants to follow up with Laura, you know, you saw her email and she's always happy to chat. I think she's a great person, but I've known her for a couple of years now, so I may be a bit biased.
I'm also on Slack. If you're on there, you can shoot me a message.
Mila? Are you on the Mila Slack?
No, I'm on the Amy Slack. Sorry.
Oh, okay. Yeah. I mean, I think we could probably add you to the Mila Slack, but all right.
Okay. Thanks, everyone.
Awesome. Thanks.
Thank you.